I'll explain HumanPlus as if I'm presenting it live to an informed audience, a single, continuous expert narrative that walks through each of the 10 points you requested in order. HumanPlus was created by a research team at Stanford University led by Ziping Fu, Qingqing Zhao, Qi Wu, Gordon Wetstein and Chelsea Finn, and developed as a full-stack research system combining hardware and learned control software. The project is documented on a project website and in a research paper and code releases that the team published openly. The work brings together a diverse student and lab effort at Stanford AI, robotics groups to build an integrated pipeline for humanoid robots to learn from and mimic human motion. The system was invented and released in 2024. The team published a paper and supporting materials including a PDF, archive submission, demo videos and code in mid-2024 describing the idea, the training pipeline, and real-world robot demonstrations. The inventors, motivation and timeline are clearly spelled out in the June 2024 paper and on the project website. Development followed a sim-to-real approach where large-scale reinforcement learning in simulation was used first, then transferred to a real humanoid hardware platform for live shadowing and autonomous task learning. At the core of HumanPlus are several main features and specifications that make the system distinct. It is a humanoid robot platform capable of shadowing, real-time following of a human operator's whole body and hand motion using only a single RGB camera, and it can transition from shadowing to autonomous skill execution learned from the human demonstrations. The research robot demonstrated a whole-body system with roughly 36 degrees of freedom. Public descriptions mention a 3-3DOF configuration, 2 dexterous hands, real-time pose estimation at approximately 25 Hz from video, and an actuator control loop running at higher frequency. Examples mention a 50 Hz controller. The software stack includes a learned low-level whole-body control policy trained on approximately 40 hours of human motion data in simulation, plus higher-level imitation transformer modules for retargeting and task learning. Physically, the body structure and materials used in the published HumanPlus hardware are described as a research humanoid built to be robust enough to demonstrate dynamic motions: boxing, table tennis, jumping, shoe tying, folding clothes. The team released hardware designs and code as part of an open repository, hardware codebase referenced on GitHub, and the robot's mechanical design follows conventional humanoid architecture: articulated limbs with multiple actuated joints, a torso, neck and head for the camera, and dexterous hands. The PDF and code release show a robot built from off-the-shelf actuators and custom linkages, typical research practice, though the team's publications focus more on the full-stack learning and control results than on detailed CAD material bills of materials in the paper. How HumanPlus works is central to the contribution. The pipeline starts with visual input, a single RGB camera observing a human, and whole body and hand pose estimators run on that video to produce a stream of human body and hand poses. Those poses are retargeted to the robot using learned transformer modules, the humanoid shadowing transformer and humanoid imitation transformer mentioned in the code base. A learned low-level controller, trained in simulation with reinforcement learning on large motion datasets, handles balance, contact, and the detailed joint commands required for whole body motion. The sim-to-real transfer enables this controller to run on physical hardware. Sensors used in the real robot include the RGB camera for perception and proprioceptive sensors, joint encoders, forced torque sensing where available, for closed-loop control. Actuators are standard robot joint motors driven by the learned policy. In short, perception: right pointing arrow; pose estimation: right pointing arrow; transformer retargeting: right pointing arrow; low-level whole body policy: right pointing arrow; actuator commands, enabling both real-time shadowing and autonomous skill learning. The team does not list a retail price for HumanPlus because it is an academic, open research platform rather than a commercial product. The project is released open source for research replication and extension. There is no single cost published for a complete build in the paper, based on typical humanoid research hardware: actuators, custom hands, controllers, sensors and chassis. Building a comparable platform would likely be in the range of tens of thousands to low hundreds of thousands of US dollars depending on components and scale, but that is an informed estimate rather than a hard figure from the authors. The public materials emphasize accessibility and open release rather than selling a finished product. HumanPlus's country of origin is the United States. It was developed at Stanford University in California and publicly released by the Stanford team. The future benefits and applications for humanity are broad. By providing a pipeline for humanoid robots to learn directly from human demonstrations at scale, HumanPlus points the way toward faster robot skill acquisition in everyday environments. Potential applications include household assistants, folding clothes, shoeing, tidying, collaborative manufacturing where humanoid robots adopt human techniques, logistics, warehouse tasks, physical rehabilitation assistance, telepresence with more natural motion, and use as a research platform to accelerate learning-based whole-body control. The ability to learn from human data could dramatically shorten the time needed to teach robots complex, dexterous tasks that today require either manual programming or expensive teleoperation. There are several hidden or less known facts worth highlighting. First, much of the capability depends on the large simulation training and a robust sim-to-real transfer strategy rather than exotic sensors. That is, the clever combination of existing datasets approximately equals 40 hours of human motion, and modern RL transformer architectures is what unlocks shadowing. Second, the project deliberately publishes code and model implementations, humanoid shadowing transformer, humanoid imitation transformer, so the advancement is meant to be reproducible and extendable by other labs. Third, while demos show striking behaviors, boxing, piano, ping-pong-like motions, the performance envelope still depends on robot morphology and actuation limits. The human left-right arrow robot physical gap remains an active research challenge. Looking forward, possible future developments and impact include more compact and affordable humanoid platforms using the same learning pipeline, improved hands and manipulation abilities learned directly from human demonstrations, integration with language and task planners for higher-level instruction following, and wider deployment in assistive and industrial settings. If the research community and industry adopt and improve these pipelines, we could see humanoid robots that learn new household and work tasks by simply watching people perform them, a step change in scalability for embodied AI. At the same time, the societal impact will require careful work on safety, robustness, transparency of learned controllers, and policies for deployment in human environments.